Welcome to Shri Learning Academy. Let's simplify context switching. Think of the CPU as a very focused worker who can only concentrate on one task at a time. The short term scheduler, which we just studied, keeps telling this worker which task to focus on next. But simply telling the CPU run another process is not enough. The CPU needs very specific information to stop safely and resume later. That safe stopping and resuming is exactly what context switching is about. A context switch happens when the operating system decides that the currently running process should stop using the CPU and another process should take over. This decision may happen for several reasons, all of which you have already seen indirectly. The time slice of a running process may expire in a preemptive system. A process may request an IO operation and move to the waiting state. A higher priority process may become ready. Or the system may need to respond to an interrupt. In all these cases, the CPU has to switch its attention. Now, let us talk about the word context itself, but in a practical sense. The context of a process is its exact execution snapshot at a given moment. It includes which instruction was about to execute next, what values were stored in CPU registers, and what the stack looked like. You can think of it as the process's mental state while working. If that mental state is lost, the process cannot continue correctly. This is where the process control block comes back into the picture. During a context switch, the operating system saves the current context of the running process into its PCB. This is not about storing long term data like memory allocation or open files, which you already understand. It is about storing short term CPU related information so the process can resume later without confusion. Let us use a simple real world analogy. Imagine you are reading a book and suddenly get a phone call. You close the book, but before doing that, you place a bookmark at the exact line you were reading. That bookmark represents the saved context. When the call ends and you return to the book, you do not start from page 1. You open it at the bookmark line and continue smoothly. Context switching works in the same way. The operating system places a bookmark for the current process and then loads the bookmark of another process. Once the context of the current process is saved, the operating system loads the context of the next process selected by the scheduler. This loading step prepares the CPU registers, program counter, and stack so that the new process can continue from where it previously stopped. Only after this loading is complete does the CPU resume execution in user mode. One important thing to understand here is that during a context switch, the CPU is not executing user code at all. It is busy running operating system code in kernel mode. This means context switching always has a cost. Time is spent saving and restoring context instead of doing useful application work. This cost is called context switch overhead. This overhead is the reason why operating system designers are very careful about how often context switches occur. If switching happens too frequently, the system spends more time switching than executing real work. On the other hand, if switching happens too rarely, some processes may wait too long, making the system feel slow or unresponsive. This is why scheduling policies and time quantum values are so important, something we will analyze deeply when we study CPU scheduling algorithms like round robin. Let us connect this to an example involving I/O. Suppose a process is playing a video and suddenly needs to read more data from the disk. Disk access is slow compared to CPU speed. The operating system knows that keeping the CPU idle during this wait would be wasteful. So it performs a context switch, saves the video player's context, and gives the CPU to another ready process, maybe a background file compression task. When the disk finishes reading the video data, an interrupt occurs. The video process becomes eligible again, and at some later time, another context switch brings it back. From the user's point of view, the video continues playing smoothly. Another important point is that context switching is not the same as process switching at a conceptual level. Process switching is the decision part, handled by scheduling logic. Context switching is the execution part, the physical act of saving and restoring CPU state. Scheduling decides who should run next. Context switching makes that decision possible in practice. It is also worth mentioning that context switching becomes even more interesting when we move to threads in the next module. Switching between threads of the same process is usually faster than switching between different processes because threads share the same address space. But the core idea remains the same. The CPU still needs to save one execution context and load another. Another subtle but important detail is that context switches are triggered by interrupts. Timer interrupts, IO interrupts, and system calls all play a role. This ties context switching back to earlier discussions about kernel mode and user mode. User programs do not perform context switches by themselves. The operating system does it on their behalf, ensuring protection and stability. To make this concrete, imagine a system running a text editor, a music player, and a browser. You type a character in the editor. A timer interrupt occurs. The OS saves the editor's context. The scheduler selects the music player. Its context is loaded. Music playback continues. Another interrupt occurs. The browser gets CPU time. All of this happens many times per second. The reason everything feels smooth is not because processes run together, but because context switching is fast and precise. In summary, context switching is the backbone of multitasking. It is the low level mechanism that allows the operating system to pause one process, remember exactly where it stopped, and resume another process safely. It works closely with scheduling decisions, relies heavily on the process control block, and operates in kernel mode using interrupts. While it introduces overhead, it dramatically improves CPU utilization and system responsiveness. As we move forward into interprocess communication and threads, you will see that many advanced features of an operating system are built on this simple but powerful idea of saving and restoring execution context. That is it for this video. See you in the next one.